Okay, everyone. So this is our final class, our final lecture. We have labs this week, though. So hopefully that'll be enough time for any of you that are not finished with Lab 4 yet to finish up. As a reminder, Quiz 6 is posted, and that will be due on Friday by midnight. The final exam will be next week. You could take it anytime next week from Monday to Friday, and you just take it on Dropbox, on Moodle. It's 25 questions, and you'll have 2 hours to take it once you start. And it will cover everything that we've talked about this semester. And then make sure that you submit and demo your Lab 4 by December 2nd, so by Friday. Okay? So last time we were talking about digital building blocks. I think we got through the multiplier. So the building a multiplier basically requires that you take the multiplicand, one of the two numbers you're multiplying, and you have different shifted versions of it added up, summed up. And so if you associate the second operand with the multiplier, then each of the 1 bits in the multiplier represents how many bits you need to shift the multiplicand and sum up those shifted versions of the multiplicand. You guys with me? So if I'm taking here 5 times 7. So I'm going to say 5 is my multiplicand and 7 is my multiplier, and of course I could, swap them if I want. So 7 means that the fact that the multiplier is 7 and it has a 1 in the 0th, first, and second bit position, or bit 0, bit 1, and bit 2, that means that I take the multiplicand and I shift it by 0 bits, by 1 bits, and by 2 bits, and then just add those up. Add those 3 things up. So that'll take 5. Okay, so that's 5 plus 5 shifted is 10, plus 5 shifted twice is going to be 20, right? So 5 plus 10 plus 20 is 35, which is 5 times 7, right? So one way you can deploy that is you can create an array. In this case, this is showing an array of full adders. So each one of these shapes here is a full adder. Single bit adder. And so you've got A, which is your multiplicand, and B is your multiplier. And B is being fed into these AND gates. And those AND gates is basically having a copy of A or zeros, right? Based on each of the bit positions of B. So in this case, B bit 0 is being fed into the second input in each one of these AND gates at the top, right? And so we're going to take A bit 0, bit 1, bit 2, bit 3, which is the multiplicand, and each one of those is being fed into an AND gate along with B bit 0. So B bit 0 comes into this AND gate, into this one, this one, this one, and this one, right? And then you have B bit 1 is being fed into another set of AND gates. So this way, what you're doing here with this first layer of adders is you're adding together A and with bit 0. So A, the value of the A, all the bits of A, ANDed with the single bit value of B0, right? And you're adding that to A ANDed with bit 1, but that one is shifted 1 bit to the left. Does that make sense? So bit B0, right? So B0 is feeding into this AND gate, which is giving you product bit 0. And then B0 is also being fed into this AND gate, in which case it's being ANDed with A0, and this AND, and then B bit 1 is being fed into this AND bit, which is being ANDed with A bit 1 and A bit 0. Sorry, it's kind of confusing. So a bit 0 is here, right? And a bit 1 is going into this one, or at least it should be. Right, because we want to be able to add, so you can see that here, right? You want to be able to add a bit 0 B0 with a bit 1 B0 with a bit 0 B1. That makes sense? So this array of adders is directly implementing this pattern of adds. So you take each of the bits of A, so A3, A2, A1, A0, and each of those is being ANDed against B0. And then those same bits are being ANDed against B1, but shifted over to the left by one position, right? And then the same thing with B bit 2 and B bit 3. That makes sense? So in order for this to work, you end up having to go through, this is a 3-bit multiplier, or I'm sorry, a 4-bit multiplier, 2 4-bit operands, and you're getting an 8-bit product. But you have to, the propagation delay here would be going through four adds, right? But that only requires actually 3 adders, because there's only 3 layers of adders here, even though it's 4 bits. And the reason for that is because the first add is, these first 2 rows are being taken care of by that first row of adders in the hardware. And then these next 2 rows are being handled by these 2 rows, right? And the reason for that is because the first 2 things you add together, you just add them. But then when you add the third item, you have to add the third item to the sum of the first 2. Does it make sense? So the critical path here is 3 adders for 4 bits, for the 4-bit multiply. Does it make sense? When I say critical, these are arranged in a way where you're seeing the path flowing from top to bottom. So you're having to go through these 3 layers of adders. Does that make sense? Okay. Okay, and then finally, for division is a little bit more complex. And the reason for that is because you have to think about how you do division in grade school. So if you have a binary number, in this case we want to have 8, and we want to divide that into, 3, 4, 5, 6, that's 64 plus 10, 74, I guess, right? So this is 8 into 74, right? So the dividend is the numerator, right? It's the number you're dividing into. And the divisor is the denominator. And then the quotient is the quotient, is the result. And then of course you have a remainder, right? So if you're doing this like in grade school, you would set it up like this, and then you would, basically what this relies on is you placing a digit above a certain digit in the dividend, which is the leftmost position you can put it in to multiply something in the quotient by the divisor and then subtract that from a shifted version of the dividend. So in this case, I take 1 and multiply it by 1, 0, 0, 0, and I'm subtracting it from 1, 0, 0, 1, right? So it relies on the positioning of these digits, right? You guys with me? Right? So it's binary. So obviously, I'm looking for which position can I place this first bit of the quotient in order so when I multiply the divisor by 1, I can bring it underneath the appropriate spot on the dividend. Does that make sense? And then of course you subtract and you get 1, and then you add zeros to bring down digits from, you bring down the first digits and it's 2, and that's not, that's less than the divisor. So you say 0 there, and then you bring down another bit, and that's 1, 0, 1. That's too low. You put another 0, and then you get 1, 0, 1, 0, and then 1, right? And then you can subtract your dividend, right? So it's basically like a variation, a binary variation of just grade school long division, right? Now, that seems straightforward, except the problem is that in order to do that, you have to sort of have human intuition to know where to start putting digits in your quotient, right? I know I can put a 1 here just because I know that that number kind of lines up with that 1000 lines up with 1001, and I can subtract that, right? I could subtract 100 from 1001, right? But the hardware doesn't know that. And so the idea behind the way division works is that it uses an algorithm called restoring division, where it tries every position for the quotient. It tries a 1 onto every position. So it'll put a 1 above that first digit, in which case it's going to have to subtract 1, which is the first digit of the dividend, 1 minus 8, right? Which it can't do. So it'll undo that subtraction and put a 0 there as the leading digit of the quotient. So I showed that, I try to show that here. So what the hardware will do is it'll try to put a 1 in that position. And then it'll try to subtract 1 minus 8. And because the result of that subtraction is negative, it's going to basically undo that. It's going to throw away that result. And it'll end up putting a 0 in the quotient, and it's going to try to put a 1 in this bit position, in which case it's going to try to subtract 8 from 2. And that's going to fail. So it's going to undo that, and then it's going to try to put a 1 in the third bit position, in which case it's going to try to subtract 8 from 4, which doesn't work. So then finally, it's going to get to the fourth bit. It's going to put a 1. So 1 is going to, obviously 1 times the divisor. So it's going to subtract 9 minus 8, in which case you have 1. Now once that happens, then it changes, the divisor gets changed. I'm sorry, the dividend gets changed. The dividend gets changed. So here it was what did I say, 74, 100, 1010, I think it's 74, right, in binary. But now I'm going to change it to 10. You might say, well, why would you change the dividend? Well, because it changes the dividend, so it has what it's doing is keeping track of a running remainder, right? So as soon as it's able to subtract a shifted copy of the divisor from the dividend, then it changes the dividend into a new value, which is the running remainder. This is a remainder now of 10 that I have left over after having put a bit of 1 in that position in the quotient. You guys with me? Right? And so then I'm going to try to, again, subtract 8 from these bit positions here, which is 2. It'll be 2, basically taking this 2 out of the current quotient, which is actually called the remainder register. And it's going to try to subtract 8 from 2, which will fail. So we'll end up putting a 0 in that position. And then it tries to do that again, and then eventually it gets to where once you're in the last bit position, you're going to take the 10 and subtract 8 and get 2, which will be your final remainder, right? So this is going to be a quotient of 9 with a remainder of 2, right? Makes sense, right? 8 times 9 is 72, and we're dividing into 74, so there would be a remainder of 2, right? Does that make sense? So basically the idea is that you can shift the quotient, you could shift the divisor to the left relative to the dividend, or you can shift the dividend to the right relative to the quotient. But either way, the point is that you're taking shifted versions of the divisor and subtracting it from the dividend, which is actually put into a register called the remainder register. So you start out with a remainder register, and you initialize that with the dividend, and then you keep trying to subtract shifted versions of the divisor from that register, and every time you're able to successfully subtract, you shift a 1 into the quotient register, and you update the remainder register. However, if you can't subtract it, if the result of the subtraction is negative, then you restore the remainder back to what it used to be. It's called restoring division. Hopefully you probably talked about this algorithm in 212. Or hopefully you did. What's the bottom line? The bottom line is you have to go through multiple iterations to solve the division problem. So it's basically, remember the multiply is essentially shift and add, right? The divider is shift and subtract, except in addition to having to subtract, there's an extra complication involved where you're subtracting, but you're having to sometimes restore the subtraction, right? Which is why this is more expensive than doing the multiply. Yes?
So the algorithm is, we're always seeing if we can put a 1 in there somewhere. And every time we subtract and get a negative value, we put a 0. It's like, all right, I can't put a 1 here, so I'm going to put a 0 instead.
Right.
And then we shift both the place we want to put a 1 in and the divisor over to the right. And then we try again. And if we fail again, we put 0, we shift. If we succeed, we put 1 and shift.
Yep. Yeah, you're always shifting this, the divisor relative to the quotient. You start the divisor off to the left-hand side, shift it to the left, and you shift it to the right. And every time you shift it right, you try to subtract. If you succeed, like you said, if you succeed in the subtraction, you shift a 1 into the quotient. If you don't, you shift in a 0 and then undo the subtraction,
and
right?
By succeed and fail, we mean we fail if the result is negative.
Right, exactly.
Otherwise succeed.
Right. Yes?
And we might not put a 0, we might not put a 1 in that last one. Like if we didn't have a 1 in bit 3 right there, then it would be 1 0 0 0, or like we would end up with a 0 in the last position instead of a 1.
No, because actually you could still do that subtraction. You'd end up with a remainder of 0 in that case. Because what would happen is if that were a 0 there.
No, bit 3.
Oh, this one?
Yes.
Yeah, you're right. Yeah. Yeah, exactly. Yeah, if that were 0, then you'd have a remainder of 2. So that would have been 8 divided by 62, I guess, right? Or no, 74 minus 8, right? Which would be 66. Yeah, you would have had 66. So you would have had a quotient of 8 because, divisor's 8, quotient 8, 8 times 8 is 64. And the remainder would have been 2 because you were dividing into 66.
You could fit 1 less 8 in there.
Right. Yes?
I just wanted to make sure I understood the inclusion of the first 3 steps, like the top row, the first 3 entries, because if I were at home doing long division, whether base 10 or binary, I would skip that and I would align the 1 0 0 0 with 1 0 0 1. Is the reason that they're included, like the algorithm isn't going to skip past it, it's going to check like basically that there's, what is the algorithm doing in those first 3?
Well, it's doing trial and error because as a human being, yeah, you would skip those steps because they would look unnecessary, right?
Yeah.
But the hardware doesn't know that, so it has to go through every possible position of this. It has to take the divisor and it has to subtract every possible position of that from the dividend.
1-bit divisor. It could just be 0 0 0 1 instead of 1 0 0 0.
Yeah. In which case, if that were the case, then you could have actually had a 1 all the way out there. Like, you know what I mean? Like this version of it would have succeeded because you would have had 1 here, and 1 times 1 is 1, and 1 minus 1 is 0, and you'd have been fine. In that case, you would have had 74 divided by 1, and the quotient would have been 74 with a remainder of 0, right? So yeah, so that's why you have to. That's a good example of why you have to start. The hardware has to start from all the way on the left-hand side.
to catch those sort of edge cases.
Yeah, exactly.
What does it do with 0 for the same reason?
If you divide by, the hardware would have to have a catch for that.
Okay.
If you divide by 0. What you'd end up with is all ones. You'd end up with all ones with a remainder of 74 if you divide it by 0. This hardware design would give you a quotient of all ones, which would have been 7 1, so 127, I guess. So it would give you a quotient of 127 and a remainder of 66, which the hardware would then have to catch as a divide by 0 error. Okay, so the book has this divider design. I don't know how common this arrangement is, but it's pretty neat. They set it up as an array of these boxes. And each one of these boxes is this hardware. And that hardware is an adder, which is actually a subtractor, because you'll notice that if you look inside these boxes, the carry in into the adder is set to 1 always, hard-coded to 1. So I always have a 1 carry in. And then the B input is, the B is negated. You see the B, you see the little bar above the B's up there? Right, so B is the denominator, it's the divisor. Guys with me? B is the divisor, and I'm subtracting the divisor. So this adder, even though there's an adder, but it's actually working as a subtractor because I'm taking the 2's complement of B, essentially, right? Okay, now additionally there's a mux, and the mux is what does the restore. So the adder is going to subtract R minus B. R is the remainder register, which, as I mentioned, is really the dividend. It starts out as the dividend, but it's really the remainder because you whittle away at the dividend until you end up with the remainder at the end. So R is the remainder, B is the divisor. You subtract them, and then D is the difference. And if the difference is negative, then this mux will switch and it will restore the previous version of the remainder, the R, right? So this R prime is either going to be R coming in. The output R is either going to be the input R, or it's going to be R minus B, depending on whether you were able to successfully subtract without getting a negative result. Okay? Okay, and then you've got carryout. So what is carryout used for? Carryout is used for calculating the quotient. And so the carryout is going to indicate whether the subtract gave you a negative result or not. Okay? Okay, so the way these are arranged, it's kind of interesting. Look at the first row. It's A, or the original remainder, is 000A3. So this is a 4-bit divider, right? So A is the dividend, the numerator, right? The number we're dividing into, and I'm putting in 000A3. So what that means is I'm taking A and I'm shifting it to the right. Right? Now you might say, wait a second, I thought you were shifting left in this case. Yes, I was shifting the divisor to the left, or you can shift the dividend to the right. It doesn't matter. It's the same either way. It's basically shift the divisor to the left of the dividend, or the dividend to the right of the divisor, right? You guys with me? Now the advantage of shifting the dividend to the right is that the subtractor only needs to be 4 bits. Okay, so basically if my B here is 11, right? 11 is what? 1, 0, 1, 1, right? Then that first stage is going to be just 1, right? Because I'm shifting that 1, 0, 1, 1 all the way to the 3 bits to the right, so I just have 1. And so I'm going to take 1 minus 5. Right? 1 minus 5 is negative 4. So the mux will then restore when that b value comes to the next stage, or sorry, when that remainder value comes to the second stage, the second row of boxes, it's going to get restored. It's going to get restored, right? Now, does it get restored to 1? Well, no, it actually gets restored to 2, because in addition to restoring the original value of 1, it also does this left shift deal, right? You see these diagonal wires here. So the value coming out of this third column is going to go into the fourth column. The value coming out of the first column is, the second column is going to go into the third column. You see that? So what ends up happening is that this thing is going to restore the original dividend, shifted dividend, which was 1. It's going to try to subtract the divisor and fail, and then it's going to restore it back to 1 again, except in addition to that, it's also going to shift it to the left. So that remainder register ends up being 2 on this second row of boxes. So now I'm going to try again. I'm going to try to take 5 minus 2. I'm going to get negative 3. So I'm going to again restore the remainder back to its original value of 2 and shift it to the left by 1. So that'll become, by the third row, it's going to become 4, except not 4, it's actually going to become 5 because it's going to bring in that 1 bit from the 11. You guys with me? It's going to bring in that extra, because I'm shifting the original value of 11 to the left, right? So that it brings in a 1 bit. So it starts out as 1, then it goes to 2, and then it goes to 4, except not 4, it goes to 5 because that 1 bit is part of that 11, right? So now I try to say 5 minus 5 is 0, right? So now that's a successful subtract, so that 0 then moves down, but then I shift in another bit in from the original dividend, which was 11. So 11, that 0 moves down, but the 0 moves down and shifts and becomes a 1 because it brings in the final 1 from the 11, right? The 11 in base 10. Okay, so now finally I have 1 minus 5, which is negative 4, and that gets restored. So what I end up with is, what I end up with in the remainder register is 1, right? And the quotient register ends up being 2, because it's 2 because the first 2 subtracts failed, the third one succeeded, and the fourth one failed. And so that's that sequence of successes and failures is translated to 1s and 0s to give me the quotient. Does that make sense? So really all that's happening here is that you're shifting the quotient into the remainder register as you go down, and you're trying to subtract each step as you go down by rows here, rather, in this guy. This thing is not clocked, I guess, right? Yeah, there's no registers in here, so this actually ends up being a combinational circuit. Of course, the critical path here would be, going through, I guess, 4, right? 4 of these boxes, and each one of those boxes is an adder and a mux. So you end up going through like 8 delays, where a delay is an adder or a mux. Single bit adder. These are single bit adders. Full adders. Does that make sense? Okay, so you can build a divider. There's other ways to do it, obviously. That's, I think, probably the simplest way to do it. I do restoring division. Okay, and that's where I'm going to stop for the building block lecture. And I'm going to move on now to the last topic. I'll talk a little bit about transistor level logic. And I'm only going to cover the first couple topics here because I also want to go through a review for the exam. Okay, so in this class we've just talked about binary logic, 0 or 1. But as you guys, I'm sure as you know, 0 and 1 are represent different voltage levels, different voltages, right? So generally, you think of 0 as like being ground, ground or a very low voltage, and 1 is going to be VDD, where VDD is the power supply voltage of the digital circuit. And the voltage you use for that depends on what technology you're working with. Okay, so it could be, for example, as high as 5 volts, or as low as, I think nowadays it's like 900 millivolts, I think, in a modern process. But as you might imagine, though, in practice, the voltages aren't always 0 or VDD. They're usually somewhere in between for various reasons, right? Generally because of noise. So just to give you an idea, there's different logic families, but CMOS has been kind of the standard family for, or CMOS or low voltage CMOS, and there's different VDD voltages for those different different families. But regardless of what voltage you're using, as I mentioned, if you have a gate, an output of a gate that drives the input of another gate, there's a good chance you're going to have some kind of noise affecting that wire, right? And that noise can be power supply noise, or mutual inductance, or parasitic capacitance. Different reasons why that voltage may be different by the time it reaches the receiver. So, for instance, this guy might be trying to put out 5 volts, but you may just be getting 4.5 volts at the receiving end of that wire. When is that a problem? Well, in order to answer that question, you have to look at the DC transfer characteristics of these logic gates that you're using. And so, ideally, if you have a buffer, now this is shown for a buffer. A buffer is a gate that doesn't. It's just an identity function. You put a 0 in, you get a 0 out. You put a 1 in, and you put a 1 out. So ideally, the way you might think of this is if you look at the horizontal axis is A, which is the input, and the vertical axis is Y, which is the output. So what you hope, the way that ideally this would work is if you put a 0 in on the input and then you start raising that voltage, the output voltage ought to be 0 until you reach the halfway point, VDD divided by 2. So if your VDD, say it's a 2-volt system, right, 2-volt logic system, then the output should be 0 until you hit 1 volt input, at which point the output then should go to VDD, right? And then it will stay at VDD as you increase it. But in reality, the way it works is you get something that looks more like this, where as you increase the input voltage, the output voltage starts to kind of creep up. And then at some point, the slope of that will rise dramatically, in which case it'll then level out again. It'll look something like this kind of this S-curve, right? And so if you look at the point on this curve where the slope is 1, that's called the unity gain point. And there's going to be 2 of those. There's going to be 1 and I guess 1, yeah, right here, right? So the first unity gain is what's referred to as VIL, which is the input threshold for a low, what's considered a low, right? So as long as your input is between 0 and the point at which you reach unity gain, which is this VIL, right, then that's just considered a 0 input, no problem, right? The gate will recognize that as a 0. Likewise, if your input is between the second unity gain point and VDD, that's VIH. That is the voltage of the input representing a high input. It's the lowest input voltage that's considered a high by the gate, right? That's VIL. So you have VIH. You have VIL and VIH, right? And so your goal is you don't want any voltage in between those two values, right? That's called the forbidden zone. You don't want an input voltage that is greater than VIL but less than VIH, right? Because that's when you're in this kind of linear region, right? Now, likewise, if you look at the output, though, and this is one of the nice things about logic gates, is that if you look at the output level at VIL, it's VOL. It's the output voltage of the gate when your input is VIL, right? And then likewise, you have a VOH, which is the output voltage when your input voltage is VIH. Okay, now what's nice about this is that the VIL is going to be more than the VOL, right? Because of the way the gate behaves, right? So you can expect that as long as your input voltage is not in the forbidden region between VIL and VIH, then you know that the output of that gate is going to be less than VOL or greater than VOL, less than VOL or greater than VOH. You guys with me? Okay, so what does this all mean? So this is basically what I was trying to explain. So the output, you've got the output characteristics versus the input characteristics. So the input characteristics, you'll have this forbidden zone between VIL and VIH. And the output, you'll have VOL and VOH, right? So so what you end up with then is a noise margin where you have an upper bound on the amount of noise that can be affecting a wire has to be the difference between VIL and VOL, right? Because the gate is guaranteed to be VOL or less, right? And then that value, so you've got an output of a gate being fed into an input of another gate, right? So because the output of one gate is being fed into the input, as long as the noise on the wire is less than the difference between the maximum output value for a 0 and the maximum input value for a 0, then these gates can tolerate that amount of noise, right? And then likewise, and that's the noise margin for the low end. There's also a noise margin for the high end, which is the same thing, where you want to make sure that you don't have noise on that wire that when added to that when subtracted rather from VOH, it brings it less than VIH, right? Because of course the noise can add or subtract the voltage, right? Does that make sense? Okay. Right, so we have basically just some terminology here. We've got VIH, VOH, VIL, VOL, and then noise margin low and noise margin high. Okay, so let's see, how far do I want to get into this? I've got about 30 minutes left. Actually, I'm going to switch gears now. We'll just end there and switch over to a review for the exam. So if you go to Moodle, you can see I've added this final exam study guide, and I've got questions and answers on here. So I'm going to go through a few of these and just see if anyone has any questions about this stuff. And this is supposed to give you an idea of what kind of questions to expect. These questions came from old exams. I basically just copied and pasted them here. If you looked at this, I had a version of this posted last week, and I've updated it since then to make it consistent with the material that we covered. So I had a couple older questions from MIPS that I've since replaced, and from Verilog as opposed to System Verilog. So hopefully this is all up to date now. So I mentioned we're going to be covering the, RISC-V, Verilog, architecture, building blocks, sequential logic, timing analysis, and I may have a question on the noise margins. That was the last topic. So I'll run through this kind of fast. If anyone has a question or needs some clarification, let me know. So let's make this a little bigger. Okay, so the first question here is consider the following sequence of instructions and their corresponding memory addresses. Assume the code is run on a machine that uses byte-addressed instruction memory, unlike the CPU design in class, which uses a word-addressed instruction memory. Now, what that means is that if you have a byte-addressed memory, the program counter is going to be incremented by 4, right? Because the instructions are 4 bytes each. In our CPU, we simplified that, and we just had the PC incrementing by 1. So the first, I asked several questions about this. Is the instruction at address 400,000 in hex a pseudo instruction? That's a load immediate. That is a pseudo instruction. It just gets translated to an add I. Is the instruction address 400,010 a pseudo instruction? That's a branch. And is branch a pseudo instruction? In RISC-V, it is. It gets translated to a jump and links into register 0. Now that was not true. That's kind of a tricky question though, because that would have also been true in MIPS too though, right? Because in MIPS, you guys remember in MIPS, there was a jump instruction, but there was no branch. All the branches were conditional in MIPS, as they are in RISC-V. Only the jumps are unconditional, right? So if you have now in this case it says B label 3, that's obviously an unconditional branch. It doesn't exist in the hardware instruction, so it becomes a pseudo instruction. Now you might ask, why would they provide a pseudo instruction for branch? I think they do that just for compatibility, because other machine languages, assembly languages do have unconditional branch, right? I think ARM does, as a matter of fact. But anyway, is the instruction address 400,014 a pseudo instruction? That's a jump register. That is not, I don't believe. That's a real instruction. Although in RISC-V, oh no, I'm sorry. In RISC-V that is, I take that back. In RISC-V it's a jump and link register, right? With register 0. So it does get translated. And then how many times is the branch at address 400,008 taken? This is starting this register 1 off at 5, and then it decrements it each time through this loop. And the branch is going to be taken as long as register 1, which is that value that's being ticked down, is greater than or equal to 0. Right? So it's going to happen 5 times, I believe. Right? Oh, it's going to go through the loop 5 times, but on the last iteration, it's on the last iteration, it'll start out at 5. At 4, it'll take it 3, 2, 1, 0. Yeah, so it'll go through 5 times. It'll take the branch 5 times because it's going to include 0 because it's branch greater than or equal to 0. Right? You guys see that? Okay. What's the fetch sequence for this code, assuming a 1-cycle branch or jump stall? So this is, you have to think of this as if you were debugging your lab 4, so you have to come up with a sequence of program counters that you would get. So, you know, it would go 400,000, 400,004, 400,008, and then it would fetch 400,000C, but that would be a stall, right? And so you have to consider that sequence. Okay, and then right. Okay, part 2 is system Verilog. Identify any problems. I think, you know, you have an assign inside of it always. You can't have that. There's some bit width mismatches here. To what value is the system Verilog code set to signal B when A is 1011? That's just a bit manipulation. You're just rearranging the bits there. Write a system Verilog module named parity. It receives 3 1-bit inputs ABC, produces a 1-bit output that's true if an odd number of its inputs are true. There's different ways you could do that. You could do it with an assign, you know, with a ternary operator. You could do it with an always com, with an if statement. You could do it with a case statement. So there's different answers for that. Convert the behavior of the following. And by the way, the exam will be multiple choice, like the midterm was. When I wrote these questions, this was back when I just did a paper-based exam, but you can expect similar types of questions, but you won't have to actually write the code out, obviously. Convert the behavior of the following Verilog module to a truth table. I think that one is, you have to essentially follow the logic here. So this says if A bit 2 is set, then Y is 1, 1. So what that means is in the truth table, you're going to have 8 rows because A is, it looks like A is 3 bits, right? Yeah. 3 bits? Yeah, A is 3 bits. Input logic 2 down to 0A, right? So the truth table will have 8 rows, but because of that if statement, that means that 4 of those rows are automatically going to have an output of 1, 1. Right? Just because we look at the first bit, and that covers 4 rows of the truth table. And then, of course, you have to deal with the other 4 rows below. Write a system Verilog module named minority. It receives 1-bit inputs ABC. It produces 1-bit output Y that's true when at least 2 of the inputs are false. It's a similar type of thing. Just, again, this is combinational logic. Write a self-checking test bench for this module. That's when you're going to use, the self-checking test bench will use an initial block to set the inputs, use delays, and then check the corresponding outputs. Everyone clear on that? Guys all comfortable with that? I had a lot of questions about Lab 3 and how do you write a test bench for the CPU. That's tough, right? I don't know how you guys handled that. So self-checking test bench is hard because you can't see what's inside. Like a self-checking, the problem with the test bench is the test bench only has access to the information that's on the top level inputs and outputs of the DUT, the design under test, right? That's an issue, right? Because of course, with the CPU, you could have a CSRRW instruction after every instruction to expose what you just calculated in each register, right? So you can have an add, CSRRW, subtract, CSRRW, and CSRRW. And that way the CPU will be kind of putting out the value from every instruction. And then you could do a self-checking test bench that would check the output of the GPIO out. That's one option. But it's kind of tough to, sometimes it can be hard to write a self-checking test bench. In this case, this is a simple circuit, so you're just, it's just essentially a truth table. So you're just checking all the rows, the outputs of the truth table. Okay, what's the purpose of the sensitivity list and an always statement? That triggers the always statement whenever anything in the sensitivity list changes. By the way, I have all the answers in the other document. I'm not showing the answers here, but there's another document that has the answers in here too, so you can use to study. Blocking assignments, update the assigned values immediately, while non-blocking assignments update the assigned values after all the actions associated with the current event is completed. How many clock cycles of delay will the code below impose? This is a page break here. But basically, inval is going to go into A on the clock edge, and then the second line there where A or B gets A will happen on the same edge of the clock, right? So on a clock edge, these two lines will kind of work together as if they'll be chained together, right? Because of the blocking assignment there, right? And then the next two lines is where C gets B and D gets C, but C gets B on a blocking assignment, and then D gets C on a non-blocking. So what will happen is that if you're looking between inval and D, so inval goes to A goes to B, B goes to C, C goes to D, but it only requires 2 cycles for that, even though there's 4 assignments, because 2 of the assignments are blocking assignments. So they sort of, they happen instantaneously, right? Okay. Sketch the hardware that the following system Verilog module implies. Basically just 2 gates kind of chained together, right? OR gate and an AND gate. But there's a catch. It's in an always FF pause edge clock, so there's going to be a register at the end of that, right? That last gate will feed into a flip-flop. Assume the following Verilog module. How many total bits comprise the inputs? Pretty much just 2 bits input, 1 bit output. Fill in the missing values for the test vectors. Test vectors are when you have inputs and expected outputs together, right? Those are test vectors. In this case, the test vectors are it just looks like a truth table, right? So you're basically, each test vector is a row of the truth table. Assume the following module, which instantiates the module above. This is kind of a confusing, needlessly confusing question. But this is some structural Verilog that instanced the module I had above, but it's renaming A, B, and C kind of get scrambled through the pin out, right? So you have to consider the renaming happening there. Describe any problems with the module below. So this is an easy mistake to make, and this is something I find this very difficult to explain in this class. It's really hard to explain what's going on here, but there's two always statements, but they're inside the same module, and both always statements are setting the value of B. Now, you would think that would be fine. I mean, in any other programming language, I think that would be perfectly valid, right? But the problem here is that those always statements, each of those always statements are generating a separate circuit, logic circuit, logic element. What's the name? Digital logic circuit, right? Each one of those always is a separate circuit, and each one has a separate driver that's driving the B signal, right? So it's like, you've got like basically two amplifiers that are being the outputs are being kind of tied into the same wire, right? So that's double driving B. Now, if you had those, if that was all part of one always, it would be fine. But the fact that you've got B set in two separate always that's the problem, right? And to make matters worse, sometimes you won't get an error because of that, and you may not even notice a red X in the simulation. As long as those two always are in agreement, they're both setting B to the same value, then you may not even notice a problem here, right? Although I think Quartus will probably choke. If you try to run that through Quartus, it might give you an error. But ModelSim won't. I don't think ModelSim will be fine with that, right? But the problem is that these are contradictory statements, because this one says if A is 1, B is 0, and if A is 0, B is 1. So actually they're not, except they have latches implied in here as well. So I'm not actually sure what to expect from that. But that's the problem. It's a conflict. It's a potential conflict, right? You don't want to do that. I think that's the only issue, actually, with that. I think that's the only problem. Now, notice the syntax is a little different. I have always at star. So this, I forgot to update this. This is Verilog as opposed to system Verilog. In system Verilog, you would say always comb. In Verilog, it's always at star. It's just equivalent to always comb. But I need to update that because I didn't teach this syntax, but the syntax there is actually okay. Star means that anything, star is like saying any potential input is in the sensitivity list, right? Where, of course, in this case, the input is, there's only one input, A, right? So star is, A is being substituted for star, but it's being done by the compiler, okay? Okay, sorry, what was the other question? Describe the process by which a user-entered HDL design is converted to a form that may be loaded on an FPGA. It's synthesized and then placed and routed, right? There's actually mapping in between, but the two important steps are synthesis, which is what parses the Verilog code and converts it to a gate level schematic, right? Or a primitive level. It doesn't have to be gates. It could be any primitive, whatever you consider primitive to be, a LUT or whatever. But basically, it converts the Verilog to a graph. A graph, which is a schematic, which is primitives connected by wires. So whatever your primitives are, gates, flip-flops, adders, hardcore adders, whatever, the synthesis lowers the Verilog, the RTL, register transfer language, the Verilog down to a schematic netlist. And then the place and route is what converts that, puts that netlist on the FPGA. The reason those steps are differentiated is because converting from a Verilog to a netlist is very different from then taking that netlist and deciding where what slots on the FPGA to put each of the nodes in that graph. That's a totally different, that's a crazy NP-complete optimization problem where you're trying to, you've got this logical gates and then you got physical gates, and I got to pick logical gates and put them onto physical gates and then connect them through the fabric, the interconnect fabric. So those are radically different problems to solve, right? So those are the basic two steps. There's the mapping phase too, which is where you have mapping is kind of a problem where the netlist may assume that you can do LUTs of any size. So you may have a 10 input gate in this netlist, but you only have 5 input LUTs on the FPGA. So now I got to split the 10 input gates into multiple 5 input gates. So there's a mapping where you have to map from one set of primitives to another set of primitives. So there's a mapping step in between as well. But usually, when I ask this question, I'm usually looking for just synthesis and place and route, the two main parts. And then there's bit stream generation, where you generate the bit stream and program the FPGA. Okay, fill in the table for the module. This is, again, just looking at delays and timing. I'll just skip past that. I think that should be pretty clear. Okay, so this question is, again, I'm not going to ask you to write any code. I used to ask questions like this for the final exam. We used to have a practicum where, I would just give you a design and have you, sit down and just have 2 hours to bang it out in the lab. In this case, it's a really simple one. It just says, it gives you a pin out, clock and go are 2 inputs, and cycle 7 and cycle 11 are outputs. So how would you design this? Basically, just it's a counter, right? Whenever go is asserted, you count. And then you have a thing that checks to see if the counter is equal to 7 or equal to 11. And so it's basically consisting of a sequential circuit that counts and a combinational circuit that checks the counter. That's basically it. But the code, I've got the code in the solutions guide. Okay, and then part 3 is pipelined microarchitecture. This is the RISC-V design. I've updated this. I updated this over the weekend to be RISC-V. I used to have the MIPS version in here, and so hopefully there's no bugs. One of the things I was missing from the lecture slides was the ALU op connection between the control unit and the ALU, so I put that in. And I have another version of this same design that has the branch logic, branch and jumps too, which is down here. This is the version with the branch and jump logic. But these are, like I said, these are brand new. Hopefully, if you find any bugs, let me know. But essentially, it gives you the whole, this is the whole CPU that we designed in class. You'll notice that the dark gray are registers and the lighter gray are the combinational circuits, right? Like sign, extend, and muxes. I tried to be consistent with that. Although the program counter should also be dark gray. I thought I changed that. To double check that. I thought I changed that. I think I did in the JPEG, but I forgot to put it back in here. But yeah, it's basically the one we've been doing. And then I said write a snippet to implement the sign extend block. You guys should be comfortable with that if because you would have done it. Write a system Verilog snippet to implement the block that produces the GPIO out. That's just essentially a register with enable. And then in the following table, I love this question because this one requires you to kind of bring together all the concepts we learned about system Verilog and architecture and the pipeline CPU. This table says, mark the stage holding each of the instructions listed in each cycle, and then give the values of the control signals for each of the cycles, right? So if we're fetching the LUI in cycle 0, then we're going to be fetching the add I in cycle 1, right, while we execute the LUI in cycle 1, right? And then all you have to do for this is for the control signals, you just have to refer, like the reg write, right? You have to say, well, what is the reg write for whatever instruction is in the execute stage? Because that's the reg write EX, right? Make sense? Now, in this case, we don't know what's in EX because I don't know what's in there. It's unknown. So I would put like unknown, right? But once you get to cycle 2, you know the LUI is going to be an execute. And so the reg write is going to be 1 if the LUI writes a register, which of course it does, so that would be a 1, right? And then the reg write WB is the delayed form. So once you have this row filled in, the next row is easy. You just take whatever is up above it and you shifted to the right by one column, right? So you don't even have to look at reg right, like same thing with reg select EX and reg select WB. These are the same things, except reg right WB is one cycle delayed, right? So all you have to do in the table is just move it one cycle to the right, one column to the right, because each column is a cycle. Okay, so yeah, so I may have a question like that to ask you what the signal is in a certain cycle for a given set of sequence of code. What changes in design would allow the CPU to execute the MVPC instruction, which I made that up, by the way, move program counter, that behaves as shown below. So it copies the address of the current instruction into the register file at address RD. And so, that's a typo. That should be regs RD as PCEX, right? Yeah, so you'll have, and it's R type, right? So the answer though is just you have to get the program counter into the register file somehow, right? So you have to add the program counter to the mux, right? Now you might say, well, we already did that though for the link instruction, for the jump and links, right? You did, but the version that you guys did in the lab won't work for this though, because this instruction requires you to write the address, the program counter of that instruction, not of the next instruction like you did for the link, right? So there is a subtle difference. So in the lab you guys did PCEX is written back, right? Whereas in this case you'd want to write back PC write back, not PCEX. So you'd have to delay the program counter for a third cycle for this one, right? Because you want the address, the program count address corresponding to that instruction, not the instruction after it, right? So there is one extra delay for the program counter. Okay, how many cycles does the following code require to complete execution? This requires you to just kind of debug, this code, this should have probably been in the RISC-V section, but it's just asking you to come up with a dynamic instruction count. Yes?
Can you scroll up?
Sure.
What is, did you already say this? What is red? The go down a little bit.
Oh, for this one?
What is?
Reds, I meant, it should have been regs. That was a typo. Yeah, reg. I meant reg. Basically, the register file at address RD. Regs, yeah, I typed it too fast and I screwed that up. I updated this. Originally, this question was about adding a variable shift instruction, which in RISC-V, all the shifts are variable shifts, so I had to modify it. Okay, so this is a dynamic instruction count. I think that's pretty straightforward. Does the CPU shown above support the load word instruction? Well, of course not. We don't have a load word requires a data memory, right? We didn't add support for the data memory. Write a sequence of 2 RISC-V instructions that would trigger the register file bypass. That's basically if you read a register or you write a register and then you read to it the next instruction, right? What would happen if the register file lacked write bypassing? Then you'd have a delay. You'd have a write delay. Every write would have a 1 cycle delay before that write was reflected in the register file. So you would never be able to have any pair of dependent instructions next to each other, right? You'd have to break all those dependencies apart, which you can do. You can schedule the code to deal with that, right? But it might require you to put no ops in some cases after an instruction. Consider the RISC-V design below. Is it possible to add support for add with write logical shift? Okay, so this is actually. The ARM processor actually does this, or actually, well, the ARM v7. I don't know if ARM v8 does, but anyway, the point is that this thing, the ARM processor famously had the ability to shift to the second operand before acting on it, right? So this would add 2 registers, but before it added the 2 registers, it would shift the second one by a certain amount, right? You could shift or rotate. There was a couple different options. It was called the flexible second operand. How would you implement this? Well, basically, you'd have to add another ALU. Right, unless you changed the structure of the pipeline and you added a delay, added another execute stage or something like that, and made it multi-cycle. Actually, it would have to be if you wanted to do it with one ALU, you'd have to have 2 cycles to execute that instruction. Make sense? Okay. This question, I only have a few minutes left, so I'm gonna power through these. This one asks this one, actually, I haven't shown an example like this yet in class, but this one is tying together the idea of timing analysis and the pipelining. So it's basically asking you to determine what is your maximum speed of your pipeline CPU, based on all these propagation delays. So in order to figure this out, you have to be able to calculate the critical path in each stage, for each stage, which is the overall critical path, right? So you'll see I have it worked out, but the fetch, execute, and write back are different. They have different paths, different combinational paths in each stage. You have to find the longest one, right? And that one is your critical path, and that's going to determine your clock, right?
And this one has memory.
This one, yes, this one has memory because this one's assuming that. No, well, the memory is the fetch. Is actually, I think sorry, scratch what I said. The memory is just for fetch, the instruction memory, not the data memory. Yeah, yeah. So it includes the time to fetch. Yeah, to retrieve the instruction from the instruction memory. Yeah, not data memory. This is still referring to our CPU that we designed. Okay, what would happen if the reg select were stuck at 0? Then you'd only be able to write back whatever the first input of that mux is. Blah, 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 skip past that. Okay, so this is the 3-stage, it says MIPS, it should say RISC-V, that's another typo. MIPS CPU should be, this is the RISC-V though. I just made this figure though I took the original, like the whole CPU design, and I tried to add all the branch stuff. I think I got everything in there. Although, I guess the program, did I forget to add the program counter? Oh, no, I did. It's right here. Yeah, program counter. Yeah, I got it. I got that. I got the stall. I got the PC. I think I'm good. I think this is everything, right? This is the whole CPU. So I asked a couple questions about this, basically another table question, and that's it. And then we got sequential logic. I only did one lecture on this, but this is all conceptual stuff, but difference between combinational sequential, difference between D-latch, D-flip-flop, consider the circuit below, what's the next state logic. The next state logic is essentially whatever's being fed into the D inputs, right? And the output logic is however the output is being computed. And fill in the timing below, and then I asked some questions about setup and hold time. Here's another elevator thing. And then this question is kind of crazy. This one says it gives you the Verilog and asks you to sketch the state transition diagram from the Verilog, right? But again, it's not like I can have you sketch a state diagram on the exam, so there won't be anything quite that complex. Let's see, and then we've got timing analysis. Again, I did just one lecture on that, but I ask you to basically do the setup and hold time analysis. And then digital building blocks, I ask about the lyrical carry look ahead, and possibly the prefix adder is here. And then might have a question about like might have a question about like implementing a divider in system Verilog or something like that, right? Okay, any questions? That's the whole thing. Okay, if you have any questions about the study guide, just send me an email, and I can, or you can ask in lab, the TAs. If you don't have time in lab to demo your lab 4, make an appointment with the TAs or me outside of lab. so we can get you taken care of before the end of the week. Okay? Any other questions? Okay, sounds good. I'll probably make a couple more edits to this, just so you know if you see a change. But again, let me know if you have any questions. All right, thank you.